Hello everyone, hopefully you're doing well. In this video, we're going to start with chapter 4, exponential and logarithmic functions. Logarithmic functions actually is a different one that we would cover a little bit later. For now, let's focus on exponential functions. There is a big difference between, exponents and exponential functions. Let's say, for example, if I have, x power 2, I can say x power 2 is exponential expressions, but that's not an exponential functions. Exponential functions usually is when the exponent has a variable. For example, if I write f of x equal 2 power x, this is an exponential function. This one here is exponential functions. So exponential functions is any times you see there is a variables in the exponent. So our objectives here is really to try to evaluate exponential functions. That's the first place we're gonna start with. We're going to evaluate exponential functions. We're going to we're going to graph exponential functions. We're going to evaluate functions with base E and use compound interest formula. So those are all things we're gonna see right after. But before we begin, let's start um, with definitions. So we said that the exponential functions in itself is with base b is defined as f of x equal b power x or y equal b power x. So when we solve the equations later, you will see the big difference. So meaning, like as in examples, we can say that f of x equal 3 power x, that's an exponential function. F of x equal uh, 4 power x minus 1, that's an exponential function. F of x equal 1 half power x, that's an exponential function. So we can write y as well. Like if I have 2 power x plus 1, those are all examples of exponential functions. Now, we need to pay attention about b. Like b is the base. We call it the base where b is positive constant other than 1. So if it's 1, 1 power x would be 1. So, and b is greater than 0 and b is not equal to 1 and x is any real number. So that's what we call exponential functions. So we have different ways of seeing it. The first thing is to evaluate. We can ask to evaluate any exponential function. So for example, here I could say, let's say, let f of x equal 3 power x, evaluate f of x for x equal 2. So if x equal 2, all you have to do, f of 2 equal 3 power 2. We substitute x for 2 and it gives you 3 power 2 is 9. So we can do that. That's what we do in the next examples where we are asked the exponential functions f of x equal 42.2 times 1.56 power x models the average amount spent f of x in dollars at a shopping mall after x hours. X represent the number of hours you spend spending money in a shopping mall. What is the average amount spent to the nearest dollar after 3 hours? So meaning if let x equal to 3. And remember, you have a function f of x equal 42.2 times 1.56 power x. That means this is the functions of that express the average amount spent in a shopping mall. Now, if you substitute X for 3 because you spent 3 hours, 42.2 times 1.56 power 3. Remember, the exponent here is not for the 42.2. It's only for 1.56. In in your calculator, probably you would see one of your keys as y power x. So that means for us, y would be 1.56 power x. That means power 2. You can do that in your calculator, or because the exponents represent the number of times that factor is multiplied by itself. So if I have that number, I can also set it's 1.56 times 1.56 times 1.56. Then you would find the answer for it. So for me, doing it from my calculator and multiply with 42.2, the answer is 160.287 6. That we can evaluate as we can round down to 160. So after 3 hours at a shopping mall, at a shopping, the average amount spent is the average amount spent is $160. Okay, so that's one of the examples of how you can evaluate exponential functions. But let's say a characteristic of exponential functions of the form f of x equal b power x. In some books, you can see it's writing as a power x. A is the base. A is the base. Okay, so or B is the base. Now we have some characteristic. We know for a functions like this, the domain consists of all real numbers, and the range consists of all positive numbers range from 0 to infinity. That's very important to remember. I'm hoping you would keep this one in mind when you're looking for the domain and the range. The graph of exponential functions of the form f of x equal b power x passes through the point 0, 1, because f of 0, when b power 0 or any non-zero number power 0 is equal to 1, where b is not equal to 0. Of course, the y-intercept is 1. There is no x-intercept. So what we mean by that, if we have for any functions f of x equal b power x, we know there are uh, 3 points passing through the graph, right? Passing through the graph. We know when x is, you know what, if x is -1, you know, b power -1 would be b power -1. If we remember any number, if we have b power -1, that would be 1 over b to make it positive. So we know this point would be on the graph. And also, if x is 0, so b power 0 anytime would be equal to 1. And what is b power 1? So if x is 1, b power 1 would be equal to b. So these 3 points would definitely be on your graph at any time. So the graphs of all exponential function of the form f of x equal b power x will pass to the point 0, 1, okay, 1b and -1 over b. If b is positive, graph b of x has a graph that goes up. So this is what we mean. I'm going to encode a slide to explain this one. if we have f of x equal b power x with where a b is greater than 1, we have an increasing function graph, increasing graph that rise from left to right. Okay, so at this point, the graph would be, this is the graph. Let's take a different color. It's gonna rise from left to right like this. Okay, so that means that's a graph of f of x equal b power x, where b is greater than 1. Okay, now if you have a graph, that's if we have f of x equal b power x, where b is between where b is between 0 and 1, okay, we have an a decreasing graph that falls from left to right. So what we mean by that, our graph in this case would be falling from left to right, okay? So here, b is between 0 and 1. Here, b is greater than 1. So we have these two type of graphs. That's what we said here. If b is between 0 and 1, graph has it has a graph that goes down to the right. So this is it right there, okay? And the steeper, the smaller the value of b, the steeper is the graph. F of x equal b of x is one-to-one function, has an inverse that is a function. The graph of f of x equal b of x approaches but never touch the x-axis. Remember, we said that the range is 0 to infinity, so we don't cross the x-axis. Or if we touch the x-axis, that means we have a different asymptote. But we know usually f of x equal b power x. The y equals 0 is a horizontal asymptote that we cannot cross, we cannot touch. Now, if we have f of x plus f of x equal b power x space plus a number that is not 0, then it would be a different one. Now, let's see for that particular example. So anytime you need to graph, or first of all, remember we said any graph, any functions in the form b power x, okay, we know the graph would rise from left to right. So I know here I can construct with many points if I want to, but I'm going to take only 3 points, -1, 0, and 1. Of course, you can take 2 if you want, you can take 3, etc. But you know what? Taking those numbers is going to make it too big. For example, -1, 3 power -1, we know 3 power -1 would be 1/3. So we have a first point, -1, 1/3. And 0, 3 power 0 is 1. We have a second point, 0, 1. 3 power 1 is 3. We have 3 points. And if you want to do 3 power 2 is 9. You see, if we say 3 now, it's going to be 27. Our graph would be too big. So once we set up a table of coordinates, we need to plot those points, connecting them with a smooth, continuous curve. So what we do, okay, suppose these two lines are very straight. Now I have -1, 0, and 1. I have 1, 2, and 3. 1, 2, 3. If I want to even put 2 here, Now, let's see our point. When x is -1, y is 1/3. Let's suppose 1/3 is here. So this is our first point. When x is 1, y is 0. When x is 0, y is 1. When x is 1, y is 3. All right, so we have enough points now. I know the 2 would be all the way up there. We can say that our graph would, okay, so this would be our graph. So I think that's a very simple examples we do, but feel free to do other ones. But you follow the same. Use these 3 points because we already know the shape of our exponential functions. It's like when you graph a quadratic functions, you already know a quadratic function, that means x power 2 would be a parabola. If you graph a linear function, you already know it's going to be a line. If you graph an absolute value function, you know it's going to be a V shape. So we already know the shape of our exponential functions. That's very, very giantly important to do. Now we can transform once you know the base. Let's say, for examples here, you can graph any of these functions. For example, if I said graph f of x equal 2 power x. First, you construct a small table where you say -1, 0, and 1. You know that would be 1/2, 1, and 2. If you graph it from here with -1, 0, and 1, 1 and 2, you know 1/2 would be here for -1, 0, and 1 give us 2. Again, here, if they ask you to graph this one, you know it's going to go this way. You know, this one is again because B is greater than 1, as you can see, because I said power 2. You're going to give you an increasing functions. If they ask you to graph y equal, or f of x equal 1/2 power x. Now, as you can see, b is between 1, 0, and 1. So it's not greater than 1, but that means the graph would be a decreasing functions. Okay, so if we take -1, 0, and 1, look, if I have 1/2 power -1, that would be 2. Okay. Now, 0 would still be 1, 1 would be 1/2. Okay, so having these 3 points, if we have these 3 points, we know already like we have -1, 2, 0, 1, 1, 1/2. Now, let's graph it. You will see the difference between the other graph. Now, if we have -1, 0, and 1, we have 1 and 2. When x is -1, y is 2. When x is 0, y is 1. When x is 1, y is 1/2. So if we graph this one, decreasing, falls from left to right, because here, as you can see, b is between 0 and 1. Here, b is greater than 1. So that's why you see the difference between these two graphs. Now, let's see the transformation of exponential functions, because this is one we need to do as well. Transformation of exponential functions. In each case, c represents a positive real number. Vertical function. So we have you know, if you, first of all, what you need to do, you graph the exponential function b power x. Then you shift it c units up, or you shift it c units down if it's -c. Now, you see when it's horizontal, the c is also is in the exponent. Okay, not at the bottom, not the base, not at the base. So you can shift it C units to the left or C units to the right, okay? So it all depends of the sign, and reflections is all depends of the sign of the exponent, all right? So now, we said also, if you have a coefficient in front of your exponential function, vertical stretch the graph of f of x if c is positive, and shrink it if c is between 0 and 1. All right. Now, horizontal shrinks the graph if the constant term is in the exponent. So very often, you can see that way, or you can just construct a table. Now, here what they ask you to do, use the graph of f of x equal 3 power x to obtain the another transformation. First of all, what we can do, we're going to graph let's graph first f of x. If we graph f of x equal 3 power x, okay, f of x equal 3 power x, let's do x and y. If we take -1, 0, and 1, 3 power, that's 1/3, 0, that's 1, of course, 1, and that's 3. Now we have our 3 points when x is -1, 0, and 1. Y is 1, 2, and 3. So when x is -1, y is 1/3. When x is 0, y is 1. And when x is 1, y is 3. So this is, okay, this one is the graph f of x equal 3 power x. Now let's do its transformations. How about the transformation? We have f of x equal 3 x minus 1. So if you look at what we said here, if we have g of x equal b power x minus 1, we can shift it horizontally c units to the right. C units to the right, but you can do that. That means we can just shift one unit to, one unit because we have one to the right. But let's do this instead. You're gonna see the same. If x is -1, 0, and 1, y would be -1 minus 1 give you -2. So 2, when x is -1, 3 power -1 minus 1 give you 3 power -2. That would be 1 over 3 power 2. That's be 1 over 3 over 9. Okay, so remember it's 1 unit, we shifted. Now that's even smaller. If x is 0, we're going to have 1/3 because 0 minus 1 is -1. 3 power -1 is 1/3. Okay, and if x is 1, what you see, x 1 minus 1 is 0, so it's going to be 1. Okay, now if x is 1, all right, so look at that. We have 1. The first point is -1, 1 over 9. We're going to have 0, 1/3, and we're going to have 1, 1. If you want to try another point, you can even put 2. Like if x is 2, 2 power, if x is 2, 2 minus 1 is 1, 3 power 1 is 3. So let's do that. I can even put 2. 2 would give me 3. 1 would give me 1. 0 would give me 1/3. And -1 would give me 1 over 9. So this is the graph for us. So this is f of x equal 3x minus 1. So as you can see, we shifted 1 unit to the right. You can just shift it, or you go from 0 to 1. We go from uh, 3 to 2, okay, 2 to 3, or etc. And now, this is how we need to graph, any exponent. Now, the natural base the natural e is defined as the value that n plus 1 power over n power n approaches as n gets larger. As n goes to infinity, the approximate value of e is 2.718. Usually, we use the first three decimal digits. So it's like when we have pi. Remember, pi is 3.14, but doesn't mean it's only 3.14. It's more than that. There are trillions of digits in pi. The irrational number e approximately 2.72 is called the natural base. The function f of x equal edx is called the natural exponential function. So what we see do it's showing how a function is increase exponentially, never stop. So the exponential functions f of x equal 1144 e power 0.0325 times x models the gray wolf populations of the Western Great Lakes. Okay. X years after 1978. Project the gray wolves population in the recovery area in 2014. Now, can you check between, from 1978 to 2014, how many years is that? You need to verify that first. So because right here, if you do 2014 minus 1978, pretty sure it's gonna be 36. So it's 36 years after 1978 is 2014. So we need to let X be 36. The number of years from 1978 to 2014. So what is X? Yes, 36. So now when you have a function f of x equal 1144 80.0325x, all you need to do in that one, we need to substitute 36 for x in that functions. So we said f of 36 equal 1144 e power 0.0325 times 36. Please, with calculator, in your calculator, you should see that key. There is a key in the calculator that says, look at that, EDX, okay? So e power x, it's in your calculator. That's something you can do. I'm not expecting you to do this one by hand because it's going to be, just imagine that you do 2.72 power. After you multiply, this is gonna give you something, and still decimal, that's not something I believe you can do by hand. So at some point, we would say f of 36 is 3,686. So that's what we need to find, because they will project the gray wolf population in the recovery area in 2014. This indicates that the gray wolf population in the Western Lakes in the year of 2014 project to be 3,686 wolves. But exponential functions, why do we use them? What are we using them for? Most of the times, you would see the exponential functions is used in the formulation for compound interest. When you invest your money somewhere in the bank, in stock markets, etc., we have different types of interest. Okay, interest rate. We have simple interest rate. That means your interest doesn't produce any interest, but you have also compound interest. That's the hope of everyone to obtain compound interest. So we have two types of compound interest. After 2 years, the balance A on your account after you invest P amount of money at an annual rate R is given by the formula. So here we said if it says it's compounded annually, monthly, compound interest, meaning P is the principal, money invested. That's and A is future value, money in the account after 2 years, future value. We said R, annual rate, annual interest rate. Annual interest rate. We have T, period of investment, time, and N is the number of times per year interest is paid. Okay, so that's what we do. In some books, instead of using N, they will just say, but the most effective, the most profitable interest formula would be continuous compounding interest, and we call it A equal PERT. So if you are given three different interests and they ask you to choose one, simple interest, there is no way you can take simple interest because your interest doesn't produce any interest. But if you take compound interest, let's suppose you invest $1,000 at 5% interest rate. After the first year, your interest earned is $50. So instead of having $1,000 on the account, you have $1,050. On the second year, your interest is no longer calculated on $1,000 on the original initial $1,000, but it's calculated on $1,050. So you see, years after years, your money would increase to the max. But if you do simple interest, 5% on $1,000 invest every year. So even though you leave your money there for 20 years, every year they would give you only $50. But if you do continuous compounding interest, well, at that point, I'm pretty sure you can buy Manhattan after 200 years. Um, let's go with an example. A sum of $10,000 in invest as interest with annual interest rate 1.808%. Find the balance, I mean, what would be the future value in the account after 5 years subject to quarterly compounding. Now, let's read again and identify what is given and what you need to find. We see in these examples, they said that a sum is invested. So you know your P would be $10,000. Is invest as an annual rate 1.08%. So 1.08%, remember that that would be the R in annual interest rate. It is 0.0108. And they said find the balance, I mean find A in the account after 5 years. T is 5. Subject to quarterly compound. What we mean quarterly compound? So how often per year this interest is paid? Quarterly. Yes, 4 times a year. So it's every 3 months. So N is 4. Remember the formula to find any future value is P times 1 plus R over N, T times N. So if we want to find the future value, we take the 10,000 times 1 plus the annual interest rate over the number of times per year it's paid, time, power, 5 times 4. You just imagine you're going to have 5 times 4 is 20, power 20. If you don't have a calculator, that's going to be a disaster. So make sure you borrow a calculator or you buy one, you know, but at least you need a calculator. Okay, so we can say that this is what we're going to have on this account. If you invest $10,000 at only 1.08% interest rate for 5 years, subject to quarterly compounding, at the end of 5 years, you would have in this account $10,554.08. So after 5 years, the interest earned would be $554 and 8 cents. So that's what you're gonna have on this account. But at some point, if they, for the same problem, they ask you to find the balance in the account after 5 years, subject to continuous compound interest. Remember, continuous compounding means the future value A would be PE power RT. Now remember, they ask you to find A, they give you P, which is uh, 10,000, and R we already know is 0.0108, T is 5. As you can see, they don't say compounding 4 times, 3 times. No, it just says continuously compounded. So if you use this formula, 10,000 times E, you don't need to replace E. Do not substitute for E because you have E in the calculator. Keep it the way it is and say EDX. Remember, you have EDX, yes. Power. Those use parentheses. Usually you do 0.0108 times 5. When you do a parenthesis like this, at the end, money on this account after, okay, after 5 years would be $10,554.85. Okay, so you see, when you use compounded interest on the long run, it's way better because here the same amount but with only 8 cents, but here 85 cents. The balance in the account after 5 years, subject to continuous compounded, would be 10,554. So, well, I think we can say that's how we introduced the exponential functions. In a different video, we will come back with logarithmic functions. Let me know if you have any questions. I'll see you in a different video. Take care.